Ford here. In this video, we're looking into topic 11, lesson 2. This is a continuation of this topic outside of class, so we can just kind of go over some of the things that are discussed here. Let me say this before we get started with this lesson. Um, I should have mentioned this before, but this topic assumes that the authors of the textbook assume that you've had some experience with volumes of solids and surface area and these other concepts. They don't really go over all of the basic generic like volumes of some solids such as cubes, um, pyramids. Now they're going to touch base on it, but they the authors expect you to have a basic common knowledge of this stuff, right? You should know what these things are. And that's usually comes from eighth grade math. It's part of the eighth grade curriculum. So they just expect that you come in knowing this. So this is basically uh, beyond the basics of geometry as far as solid geometry. That being said, um, the good news is when you take the LEAP test, you won't be expected to know much more than what is covered here in this book. I mean, if anything, honestly, I doubt you would see any of these questions on the LEAP test. You may have some volume questions. I know there's always one where you have two solid shapes, one within the other, and you have to find the volume of the solid after removing the shape that's on the inside. So basically you would find the volume of both shapes and then subtract. So if you can figure out the volumes, and of course you have a reference sheet when you take the LEAP test, so that shouldn't be a problem. Find the volume, subtract the one that you're taking out, and that's usually what the question entails. All right, so the I can statement for this lesson is I can use the properties of prisms and cylinders to calculate their volumes, right? And there's three new vocabulary terms: Cavalier's principle, oblique cylinder, and oblique prism. All right, so we're going to talk about what those things are. Um, I just want to get to some of the examples right away with the definitions in them. So example 1, develop Cavalier's principle. How are the volumes of the two different stacks of index cards related? The first stack forms a right prism. The second stack forms an oblique prism. An oblique prism is a prism such that some or all of the lateral faces are not rectangular, right? So this is a good definition to have in your notes, right? And you will hear it occasionally and you'll see it in test questions and you'll say, what does oblique mean? Oblique is kind of out the ordinary, right? So as far as an oblique prism, it's a prism such that some or all of the lateral faces are non-rectangular, right? For instance, and what they're referring to is this first stack here, the face, if you were to illustrate it or trace it, you can see is rectangular, right? So if I took that, it's rectangular. But then this face here, even though it's the same amount of cards, or we assume it's the same amount, they haven't discussed that yet, but this face is non-rectangular. So if I take it up so you can see it, it's more of a trapezoidal shape, right? Okay. All right, so the volumes of two stacks. So the heights of the stacks are the same. Each index card has the same area and represents the rectangular cross section of the prisms. The volumes of the two stacks are the same because the sum of the volumes of the cards are the same. So, do you think, looking right here, do you think that the right and oblique cylinders have the same height and cross-sectional area, also have equal volume? Explain. So, the illustration and you can see where it tells you they have the same height, they have the same cross-sectional area, so do they have the same volume? Well, the question would be yes. Obviously, the same volume because it's the same quantity of cards and they take up the same amount of space. Okay, so this is kind of an introduction into oblique prisms, but it's oblique any solids, right? We're going to deal with oblique cylinders also. So, Cavalier's principle. Cavalier's principle states that if two three-dimensional figures have the same height and the same cross-sectional area at every level, then they have the same volume. Okay? Same height, same cross-sectional area at every level, then they have the same volume. And what they mean by cross-sectional area is if you were to slice any one of them, the same slice, same thickness, if the area of that slice is the same, that's a cross-sectional area. Okay, so that's what they're referring to. So now we're going to talk about the concept volume of prisms and cylinders. Of course, this is one of those things that you're expected to kind of know coming into geometry, but the volume of a prism is the product of the area of the base and the height of the prism. Notice how they put that. It's the product, right? So if you take any solid and you slice it up into equal slices, you can calculate the area of each one of those slices, but if they're all even slices, you can calculate the area of one slice and then multiply times the number of slices you have to find the volume. So that's essentially what's going on here. The volume, notice they use a capital V of a prism, right? Look, notice they use a capital B and a lowercase h. Your capital B, that's not this line here, or that length rather. It's that length times this length. So it's actually the area. So the capital B stands for the area, oh Lord, the area of a cross section, right? Of a cross section. So, and I'm going to say of the base because that's what they're referring to. The base is a cross section. So I don't want you guys to get confused. Normally, when we're talking about, the area of a rectangle, we would say, um, some people would say base times height, but it's, you can use length times width, whatever the case may be. But anytime you do that, if you notice, you should be using lowercase letters. So when you use the capital B, that stands for the area. This capital B stands for the area of that base. And then the H, of course, is the height, right? So then looking at the cylinder, same thing. Notice volume equals base times height. Well, the base is a circle. So the area of a circle is what? That's going to be pi radius squared, right? So therefore, that pi radius squared is the base of that cylinder. So it's the same thing. You take a cross-section cut of it, that's going to be the capital B base, which is going to be the area of that circle, which would be pi radius squared. Okay? So, yes, we're going to be using pi when it comes to these cylinders. We really haven't used it much this year, but we will be using it very soon with some of the new concepts we're going to get into. All right. Find the volumes of prisms and cylinders. Lenzel needs to store 20 cubic feet of firewood. Could he use the storage rack shown? All right. So now we have a triangular prism, right? This has the same thing as base times height, capital B times height. But that capital B stands for the area of a triangle. The area of a triangle, you have to remember, it's 1/2 base times height, lowercase b, right? So it's 1/2. So this one would be that 6 foot by 4 foot. It's half of that. So 6 times 4 is 24. Half of that would be 12. Then you multiply times 2 because that's the depth of that rack, right? And that's what they have here in this operation. You have 1/2 base times height of the triangle, then times 2, which is the depth, equals 24. Now, you have to store 20 cubic feet. So is a 24 cubic foot space enough? Yes. The volume of the storage rack is 24 feet or 24 cubic feet, so Lonzel can store his firewood in the rack. Looking at B, Keisha is deciding between the two canisters shown. Which canister holds more? What is the volume of the larger canister? Notice they both have a diameter of 20 centimeters. Okay? They both have a height of 25 centimeters. See this information here? That's just there to throw you off. That's not relevant. What's important is this height, this diameter, right? So notice the note. This canister is an oblique cylinder. Remember I mentioned that earlier. You'll deal with oblique cylinders. An oblique cylinder is a cylinder such that the segment joining the centers of the base is not perpendicular to the planes of the bases, right? So basically, now it would require it to still be cylindrical in shape, meaning the space, the diameter is the same throughout the cylinder, right? So this would also be 20 centimeters, right? I mean, it kind of goes without saying, but I want to make sure you guys are aware of that. All right. So the canisters have the same cross-sectional area at every height. So by the Cavaliere's principle, the canisters have the same volume. Use the volume formula to find the volume of the canister on the left. Volume equals pi radius square, remember that's your base, times your height. Now, don't get mixed up. They give it to you in 20 centimeters. That's your diameter. Your radius is half of that. It's 10. Okay? So pi radius squared times 25. So you end up with 7,854. Well, guess what? This second one has the same height and the same diameter. So it's going to have the same volume, which is also 7,854. All right, I'm going to skip the triads on these. If you want to, you can go and work on them to do the calculations, but I'm trying to keep these videos a little bit shorter just so we can get through the material and you don't have to spend your whole holiday watching videos. All right, example 3, apply the volumes of prisms to solve problems. So Marta is repurposing a sandbox as a garden and is buying the soil from her school's fundraiser. Estimate the number of bags she will buy or she should buy. All right. So these bags, well, first we need to calculate the volume of the area, right? The determine the volume of soil needed. And you would compute the volume of the sandbox in cubic inches. So it's 10 inches tall, right? You have 4 feet long by 4 feet. So it's a square box, basically 4 feet by 4 feet by 10 inches, right? But notice something. They're given in feet. Everything else is in inches. So it may behoove you to change that feet into inches. Now you don't have to start, but you'll have to eventually to solve either to, figure out how many feet or how many inches you're going to need based on feet, or how many feet you're going to need based on the inches you have. So one way or the other, you're going to have to do some sort of scaling up or scaling down. All right. So step one, determine the volume of the soil needed. Compute the volume of the sandbox in cubic inches, right? So there you go, in cubic inches. Change it to inches. So you have the volume is base, that's the area, times height. So your base would be 48 times 48 times your height of 10. So that's 23,040 inches. Now, I know it seems like a big number. I would leave it in inches because your bags of soil, it comes in inches, right? Okay. So step two is estimate the volume of the soil in each bag by modeling the bag of soil as a rectangular prism, right? So notice the illustration. The bag has a height of 5 and then a width of 10 and depth of 18, or vice versa, however you want to say it. So remember, the volume is going to be capital B times height, right? Base times height. Your height is 5, so this would be volume equals 18 times 10 times 5, right? And then you end up with a total of 900. So each bag carries about 900 cubic inches of soil. So then you have to divide that 23,000 by 900 and you end up with 26. So it's approximately 26. But notice they say Marta should buy 35 bags of soil to fill the sandbox. Why 35 bags? I wonder if that was an error on their part. Let's check something. I'm going to do 900 into 23,040. All right, so I'm going to take those double zeros off and I'm going to move the decimal 2 places. So 9 goes into 40. Well, I guess I'd have to use a 0 here. 9 goes into 2 0 times. 9 goes into 23. 2 times 9 is 18. You get 5. Bring down your 0. 9 goes into 50. 5 times 9 is 45. Then bring down your 4. So 25.6 bags, so approximately 26 bags. So I don't know why they said she would need to buy 35 bags. Hmm, maybe it was an error on their part. All right. So that's the volume of a rectangular prism, right? Or square prism, cubic prism, whatever it is you want to refer to it. Next, example 4. Apply volumes of cylinders to solve problems. Benito has 15 neon tetras in his aquarium. Each neon tetras requires at least 2 gallons of water. What is the maximum number of neon tetras that Benito should have in his aquarium? Hint, 1 gallon is equal to 231 cubic inches. All right. So height 32, diameter 16. Remember, volume is going to be capital B times H, which in this case would be the capital B is the area of the cross-sectional circle, so volume would be pi radius squared times height. You'd have pi times, let's remind you of something. This expression here, it's pi times radius squared, so it would be pi times 64, right? You have to square that radius first. Don't do pi times radius and then try to square them both. You have to square that first. So then it would be pi times 64 times 32. The book skips some steps sometimes, but I guess they figure you should know that at this point, but I just want to remind you just in case. All right, so the volume of the aquarium is about 6,434 cubic inches, right? And remember, you need at least 2 gallons of water for each neon tetras. So then 1 gallon is 231, so two gallons would be 462 cubic inches, right? So then you would just divide. So they went ahead and divided by a single gallon, which is fine. Um, and then you have a total of 27.85 gallons, but then you would divide that 27.85 by 2 and you get 13.9. So you should have no more than 13 neon tetras. Remember, you cannot have 13.9 because what are you going to do? You're going to cut a tenth of one off? No. So no more than 13. Better to be safe than sorry. Okay. Example 5. Determine whether volume of or surface area best describes size. A forest surveys giant sequoias by gathering data about the height and circumference of the trees. Should the forester use surface area or volume to describe the sizes of the sequoias? Explain. The amount of wood in a tree is represented by its volume, so she should use volume to determine the size of the giant sequoia. Now, I know you can't really tell by this illustration, but those trees, those are huge. You might be used to seeing pine trees that look similar to that, but take that pine tree and multiply it times 10, and then you'll get one of those sequoias, right? Notice the height, 270 feet. Notice the circumference, 101 feet across. That's crazy. So what are the sizes of the sequoia shown? Rank them in order by size from largest to smallest. So look, we have a height of each one. Then we have a circumference, right? That's the king of geometry, circumference. Get it? I thought it was funny. Anyway, circumference measured at 4.5 feet, right? So they, from the base, from the ground, they measure 4.5 feet in the air. And the circumference is 101 feet or 109 feet or 106 feet. Remember, that's the circumference, as if you were trying to hug that tree. That's 101 feet. If think of it this way, if you were going to tie a rope around it, you would need at least 101 feet of rope just for the ends to touch. That's probably a better explanation. All right. So what are the sizes of the sequoia shown? Rank them in order by size from largest to smallest. Although the sequoias have branches and a trunk tapers gradually towards the top of the tree, each tree can be modeled as a cylinder. Find the volume of each cylinder to estimate the volume of each tree. All right. So notice they did the calculations for us. That's great. We don't have to worry about doing that. But how did they get this here? How did they get this? We know that's radius. What about that? So if you recall, the area of a circle is pi radius squared. But what about the circumference of a circle? Do you remember what that is? That's 2 pi r, right? 2 times pi times r. Well, that 2 times r, 2 times your radius is just your diameter. So some people would say, some people use pi times diameter, right? Pi diameter. That's what that is. So they're saying, okay, well, if the circumference is, if the circumference on the first one is 101, then to find what the radius is, right? If the circumference is 101, and it'll be 2 pi r, then to find what the radius is, we just divide both sides by r, and then 101 would over r, wait, scratch that. If we're trying to find the radius, man, I don't know, it's too early in the morning, I guess. If we're trying to find the radius, we have 101 equals 2 pi r. If we're trying to find the radius, then we're going to divide both sides by 2 pi. So those cancel out, and then our radius is equal to 101. Come on, man. Why is my computer tripping? 101 over 2 pi. Okay? So that's where that comes from. Just trying to find the radius. All right, so if you look at it, you can see they did the calculations for us. In order from largest to smallest, the three trees are tree B, largest, tree C, second largest, tree A, smallest. Now, even though tree A has a greater height, it's not quite as thick. So that's why those other trees are larger. All right. Well, it's time for the concept summary. If you guys want to do the practice work, like I said before, you're welcome to do so. Um, I'm not holding it to you because this is extra. This is just trying to help you guys out before the LEAP test. So, words, vocabulary was vocabulary's principle. Figures with the same height and same cross-sectional area at every level have the same volume, right? So that's referring to those oblique prisms and oblique cylinders. As a result, right and oblique prisms and cylinders with the same base area and height have the same volume, right? So commit that to memory. The one thing you should really take from this lesson is that capital B right there. That is not the lowercase b you use for one of those. It's actually this times that. It's the product 6 times 5, right? That's what that uppercase B is for. So that uppercase B is the area, and I'll say of cross section, right? Okay, that's what you need to remember. Make sure you don't mess that up when it comes time for your test. That's going to be it for today. As always, you know I love you guys. Why else would I be doing this at 6 in the morning? Stay beautiful, stay humble, and just stay golden, my nuggets.